So let's do that for the, so you have mass times acceleration equal force. When it comes to rotation, it's I theta double dot, or which is alpha double dot, right? Equals all the moment, right? When you apply this equation, again, I need alpha, I need I about some point, this is the moment of inertia, and moment about some point. What point should I use? Or what point I have to use? What point? So this equation comes from what discipline? This is what discipline? Aerostructural dynamics. What discipline is that? Dynamics, very good. When you write this in dynamics, dynamics tells you if you write this equation, it has to be about 1 point. What's that point?
Or the piston, the pinch point, the piston.
The what?
Like the piston, like the word.
I'm sorry,
like the point where it's piston, right? It's like that the cantilever is like it has the point where it's attached, or like hinge point.
No, it has to be CG. It can be a hinge point if it's a pure rotational motion. If it's not a pure rotational motion, no, it's CG. And this is one of the things that we focus and stress on in 241. If you took 241, you remember this. It has to be about the CG. Alternatively, you can write it about whatever point convenient to you, because the CG is not a convenient point for us here. Why? Because our structural theory is about the elastic axis. We like to write this rotational motion about the elastic axis. That's fine. If you want to do that, this equation is no longer valid, and dynamics tells you the equivalent, which is the rate of change of any point P, angular momentum, which is, this is not a fancy thing, it's simply I alpha double dot about this point P, okay? This is equals to, you expect that this is the moment, right? No, it's not only the moment, but you have to account for the acceleration for that point. So if I'm rotating about the elastic axis, and the elastic axis is a stationary point, is a fixed point in space, which means that my entire motion is just rotation about this point, and this point is stationary. So that's right, you can write down I alpha double dot equals moment about CG, or about this stationary point about which you rotate. But if this point in particular is moving, because it's indeed moving, it moves with a displacement h downward, right? So it has an acceleration h double dot. So you need to add this correction term, which is mass centripetal term, mass acceleration of that point across the distance between this point to the CG. So you can see if that point is the CG, you recover the well-known equation. Okay? This is what we focus on and stress in 241. So this guy is the moment about the elastic axis in this sense. Let's get this guy. What is the acceleration of the point P, which is, the point P is the elastic axis. We'll take P as our elastic axis. Okay? What is the acceleration of that point? So this blue point, what's that? What's the linear acceleration of it? What's the linear acceleration of this point?
Minus h double dot.
Very good. It's minus h double dot in the j direction. Cross. What's the vector between the point and the CG? Well, it's x alpha b in the I direction. And here's the cross. So if you do j cross I, this is m h double dot x alpha b in the k direction, but the k direction in this sense. So our equation is I elastic axis alpha double dot equals m elastic axis in this sense, because alpha positive in that sense, and here minus m x alpha b h double dot.
Sir?
Yes,
I wish to clarify one thing. Sure. Like in that equation which you wrote down, like I alpha dot dot is equals to m, the moment equation. Yeah. So like, if I say like in a qualitative sense, does that mean like it's a moment at the CG but about the hinge point, right? It's like the moment is happening about that fixed point, but then it's acting at the CG. Like it won't be moment about CG, right?
No, I don't know. Maybe I don't get exactly what you're saying, but when I compute this moment, I will not compute the moment. I will have to compute the moment about the CG. I will not compute the moment about the point. If I'm computing the moment about the point, like here, I really have to account for the effect of the acceleration of the point. Okay. Yeah, I mean, I understand that it's tricky. If I'm rotating about this point, I should account for the moment about that point. That's right, but the point is accelerating itself. We derive this detailed equation into 41 if you like to see. I can refer you to the video. But it's one of the things that that are a little bit tricky, because this equation is very famous, and we think that it's applicable at any point we're rotating. Yeah, no, it's the CG is a very special point indeed. Also, this equation is not applicable to at any point. You cannot say mass times acceleration at any point equal force at that point. I mean, the force doesn't matter at any point. It has to be the center of gravity, otherwise it's not correct. The center of gravity is indeed special because of that for a rigid body. Okay, we got this guy. This is the total moment at the elastic axis. We have several sources for it. Let's look at our picture. Again, we have three disciplines, right? So we have here aerodynamics, and we have what else? Let's look here. I need all the moments about the elastic axis, about the blue point. So we have moment coming from aerodynamics, which is lift times that distance plus this m, whatever. But moment coming from aerodynamics. What else? What else?
Structure.
Structure, very good. What is the moment coming from structure? Can you tell me? Well, moment coming from structure means go and apply your structural theory. Our structural theory is simply k times the angle, right? And what else? So from aero, we're done. From structure, which is this torsional spring, we got it. Any other loads that create a moment at the blue point?
The bending moment, right?
The drag, I mean, we assume that the drag is collinear with that point, so it's not. If you want to do a more intricate analysis, you can account for it. What?
It's the bending moment, right? To do the bending force?
No. At a particular section, the bending moment will not show up, because the bending moment is about this axis. Doesn't show up here. The twisting moment show up here, and this is why we account for it. What else? Any other moment?
Gravity.
Gravity. The gravity, there is an offset, right? So and this moment will be positive. So this guy, we have minus mg, here is the gravity times the distance, is x alpha b. Okay. So we have two equations of motion, 1 and 2, and we want to study the stability. The steps that we're doing is exactly the steps that you will be doing in analyzing any dynamical system. In the sense that if it's an airplane, you will do exactly the same. If it's a submarine, if it's a robot, if it's a satellite, you will be doing exactly the same. Dynamic model, mass times acceleration equal forces. We've got that. Then we should ensure what? If we want to analyze stability, you cannot say stability and just stop. You have to say stability about what? Equilibrium, or what operating point. So first of all, in order to study the stability about some equilibrium point, you have to ensure equilibrium, which means we have to ensure balance. So at our operating condition, we have to make sure that it's really an operating condition, that everything balances each other. The summation of all forces equals 0, summation of all moments equals 0. So in this balance step, we replace any variable by variable node. Okay. So for this equation, the double derivatives in the left-hand side will go to 0 because it's equilibrium. Okay. And the right-hand side will just denote it by node. Our balance, our operating point of interest will be no plunging displacement, and we have some angle of attack. Okay, so h equals alpha node is not 0. So you have non-zero angle of attack. Is this the angle of attack we want to fly at? You can assume it's zero, but it doesn't matter. But anyway, let's make it realistic a little bit. So the left-hand side of 1 goes away, 0, and the right-hand side we have what? mg, we have lift at this angle of attack, it's called L naught, and this guy will go away, there's no plunging displacement. So the equation 1 will give you that mg is equal to L naught. At balance, the lift equals the weight. Yeah, we know that. Equation 2, similarly, again the left-hand side will go away, there's double derivative, and also the h double dot term. And this moment summation, this moment is 0, which means the aerodynamic moment naught minus k alpha naught minus mg x alpha b, all this is 0, right? Okay, so if I'm generating lift that is equal to the weight, and if I'm generating moment that is equal to this summation, I ensure balance. This is indeed an equilibrium point. Okay, what is the definition of an equilibrium point? The definition of an equilibrium point is that if you start at this point, you will remain indefinitely. Nothing will happen. It's an operating point. You will operate at this point. But what if I'm disturbed a little bit from that point? Will I come back or not? This is the question of stability. So as you can see immediately, the question of stability is related to perturbation. You have to be perturbed from that balance or equilibrium. So for a perturbation, we replace each variable by variable naught plus delta variable, and we know that the delta is small. So we will go to this equation and replace each thing by naught plus delta. And remember that L naught is equal to mg, so it will go away. So you will have what from here? You will have mass times delta h double dot. Can you see it in the same thing? Mass times delta h double dot. I guess it's hard for me to write like this. Okay, this is the equation that will, there is no h double dot naught, it's 0 by definition, right? Alpha double dot naught is 0 by definition. So this is mx alpha b times alpha double dot or delta alpha double dot equals, this is the left hand side, equals mg goes with L naught, so we have just delta L minus kh times delta h. Here is your first equation. The second equation, here's the second equation. This one. Again, the left hand side is I elastic axis delta alpha double dot equal. This guy, M aerodynamic naught with K alpha alpha naught with this term, they will go away, and you'll just left with the delta here and delta there. There is no delta in gravity, luckily. So this is delta pitching moment aerodynamics, K alpha delta alpha. This guy go away, and you have this term minus m x alpha b delta h double dot. This term shows up many times, so we'll call it S alpha. It represents the eccentricity between the center of gravity and the elastic center. Here is your two second equations. Now I have this system of equation. Let's write it in a more compact form, in a matrix form as usual. So here is something times h double dot. Everything is in terms of delta now, so I'll drop the deltas, okay? Plus something in h and alpha equal something. This is m and s alpha. This is s alpha on the I elastic axis. In h we have here kh and k alpha, zeros. Here we have negative lift and pitching moment. This is delta n. So you can see this lovely equation. What is it? We lump this and call it the Mace matrix, right? And this is your coordinates double dot acceleration plus stiffness matrix, your coordinates equal forces. Okay? And this is actually almost purely structural model. It's the dynamic equation of the structural model, so called M structure, K structure. So as you can see, this is indeed the structure dynamic model. What's the input and what's the output? So Q here, just you may have noticed it, but Q is just your H and alpha, your coordinates, your what we call in dynamics configuration coordinates, your degrees of freedom basically. Okay. Any question about this red equation? Please, if you have any question about the derivation of this red equation, we have to stop. If you accept it, we can move on. Any question about it? Yes, Lee?
So is there any reason why the how we ensure balance and also perturbation is the same process as we got the linearization?
Exactly. I'm looking for a linearization. This the resulting model is linear model. Yes.
Okay.
Exactly.
So there's
I'm doing linearization.
Okay.
Basically, I'm studying the linear stability. The nonlinear stability is. So let's put it this way. Even if you have a nonlinear system, I would say more than 90% of the time, the linear stability analysis is sufficient. And it's very straightforward. You got it very easy like this. You have a linear model, study its stability like I'm going to show in a minute. Sometimes the linear stability analysis is not sufficient and you need to do nonlinear analysis. This is very few cases. So even if you have a nonlinear system, this is why, because some people say, okay, we spent our entire undergraduate and most of our graduate studies studying linear systems, whereas the world is is not linear at all. The world is, everything is nonlinear. Every system is nonlinear. That's correct, but for a nonlinear system, the linear analysis is sufficient. So any nonlinear system is stable if its linearized version is stable. Any nonlinear system is controllable if its linearized version is controllable. Any nonlinear system is observable if its linearized version is observable. Any nonlinear system is detectable if its linearized version is detectable. It's stabilizable if it's stabilizable, and so and so. And where it's not, the linearized version is not, it's very, very few cases. Then you need to do nonlinear analysis, which is much harder, by the way. So anyway, so this is our governing equations of motion for the structural dynamics. Do you have any question about this? What is the input to this equation? So the system parameters are given. These are parameters. Mass and stiffness. What is the input and what's the output? What's the input?
Forcing.
The what?
The forcing.
Exactly. Structure problem, you have the forces. You have the right hand side. Okay? And you solve this differential equation to get